Here we have the piecewise function. Let's write that in. This is called a piecewise function, and this function is equal to 2x plus 4 if x is less than or equal to 1. And then it's equal to x squared if x is greater than 1. And so if we, on the graphing calculator, if we grab, we go in and we grab 2x plus 4 with no restriction, then we get a straight line like this all the way over here. But if we have the restriction x less than or equal to 1, and then the graph will stop at x equal to 1. This is x equal to 1 right here. And the reason it's closed right here, because this is less than or equal to. And then this function says that it's equal to x squared. And again, if we graph y equal to x squared with no restriction, then we get a parabola that goes like this. But this says that the x is restricted to be greater than 1. And so that's why this is 1. And then x, the function y equal to x squared, is only on the interval from 1 to infinity on this side, which is this part. And so this is called a piecewise function. And again, we want to show that the function is discontinuous at x equal to 1. And one more time, to show that the function is discontinuous at x equal to 1, we must show that one of these three conditions fails. And so first, we need to see if f of a or f of 1 is defined. So f of 1, so this is x equal to 1. And so we have to decide, do we use the first piece or do we use the second piece? And so we looked in here and in here. So this is x equal to 1, x equal to 1 is in here. And so we would use this one. So for f of 1, we use the piece f of x equal to 2x plus 4. One more time, because x is less than x is 1, and 1 is part of this x less than or equal to 1. And so f of 1 would be 2 times 1 plus 4, which is equal to 6. And therefore, the function f of x is defined at x equal to 1, because it's equal to a real number. Because f of 1 is equal to a real number. So condition 1 is met. And so next we need to find the limit as x approaches 8. So we need to verify this condition right here. As though here a is 1. And then, so we need to find this limit as x approaches 1 right here. Then we need to find limit from the left of 1 and limit from the right of 1. And so let's do the one from the left side first. And so here's the graph again. This is 1. If we are to the left of 1, then we have to use the piece 2x plus 4. If we are to the right of 1, we use the piece x squared. And so this right here, the f of x will be the piece 2x plus 4. As x approaches 1, we get 2 times 1 plus 4. As x approaches 1, 2x plus 4 approaches 6. And then we need to find, so that's the limit at x, x limit from the left of 1. And then now we need to find the limit from the right of 1. So this is 1 right here. And we're approaching 1 from the right, meaning we're to the right of 1. If we are to the right of 1, then we would use the piece f of x equal to x squared. And therefore the limit right here be x squared. As x approaches 1, then we get a 1 here, and then x squared will approach 1 squared, which is 1. So limit from the left of 1 is 6, limit from the right of 1 is 1, and they're not the same. And therefore the limit at 1, we say that does not exist because limit from the left is not equal to the limit from the right. And so condition number 2 fails. And therefore the function f of x is discontinuous at x equal to 1. And let's look at the graph again. And again, at x equal to 1, we have a gap right here, and we say that f of x has a non-removable discontinuity at x equal to 1. But if we look at the graph, other than that, the graph is continuous everywhere else. And so, except at 1. And so we say that f of x, and this is how we write continuous everywhere else at x equal to 1. F of x is continuous everywhere except at x equal to 1. And so we say that f of x is continuous on the interval negative infinity to 1, and then union 1 to infinity.